Okay, we're on page 165 in the book. They show you the derivatives of the inverse functions. The graphs of the function inverse. Okay, so that just means notice the tangent lines have reciprocal slopes. So that's what they're talking about with the derivative. But I want you to look at the slope, or I'm sorry, the derivative of the sine y, and it's actually on page 166 because we're doing the inverse trig functions and where they are derived from. So the inverse of the graph can be obtained by, yes, reflecting across the line y equals x. Okay, that's the inverse. The graphs of the sine curve, so you know the graph of your sine curve, your basic sine curve. Let me go again with this marker. So your sine curve, looks like that. That's your basic sine curve. Okay. Now, when you graph the inverse, so it shows you it goes from -1 to 1, just like this one, the original goes from 1 to -1. Okay? And it is a reflection over the line y equals x, so it goes like this. And this is -pi/2, and this is pi/2. It's restricted. Now, the reason why it's restricted and the reason why it goes from -pi/2 is because it has to remain a function. So if I take this part of the graph from 0 to pi and I reflect that over the line y equals x, what's going to happen is it fails. See how it fails? The horizontal line test. Therefore, when you reflect it, it's going to fail the vertical line test. So that's why we have to use this part over here as your inverse. And it's just a snapshot, so it's really this part right here, okay, is what is being reflected over the line y equals x. Okay, and this takes me from -pi/2 to pi/2. Okay, does that make sense? All right, so since it passes the horizontal line test, the graph is differentiable throughout the interval, or -1x to 1, okay, because those are your max and mins. So we want to find the formula for the derivative of y equals sine inverse of x. Okay, so if we want to take the inverse of y equals sine inverse of x, it is sine y equals x. That's the inverse function relationship. Okay, and what I'm showing you here is the same explanation in 166. I know it gets a little tricky. Okay, so anything you see, oh yeah, where did you get that? Okay, it's coming right down the line there. All right, there might be something that they assumed. Yeah, there is one part that they assumed that I'll show you where they got it from. Okay, for the most part, I'm following along with the example. Now, when you find the inverse, remember you switch the x and y, and then you are going to solve for y, okay, or the dy dx, right? So what we want to do is we want to take the derivative of this. So when we take the derivative, we have the derivative of sine y is cosine y, and then you have your u prime, so to speak, okay, or the derivative of y. So the derivative of y is your dy dx. So sine y derivative is cosine y. The derivative of y is 1 dy dx. Okay? And then the derivative of x is 1. So remember, when you're finding the derivative, because you're finding the formula for the derivative, you need to get the dy dx by itself, and that's 1 over cosine y. Now, we are not going to leave it as cosine y. We're going to try to put it in variables, so that way you can substitute in for the variables. And if you look in the book, what it has the derivative of the sine inverse of x is 1 over the square root of 1 minus x squared. So they just kind of throw that at you. Well, where does that come from? That's all based on your Pythagorean identities. Okay, your basic trig Pythagorean identities. So if I solve for cosine, I would move the sine squared over. So I have cosine squared y equals 1 minus sine squared y. So again, we want to solve for this cosine, so I have to take the square root. Because remember, the cosine squared y is the same thing as cosine y quantity squared. So I take the square root of both sides, and I have cosine y equals the square root of 1 minus sine squared y. Okay. And we just use the positive value. So what do we know? We know sine squared y equals x. Therefore, we have cosine y equals the square root of 1 minus x squared. Because you're substituting in the sine y as an x. Okay, does that make sense where I solve for cosine y? So I'm just giving you the validation of where the formula comes from. I could very easily just say, okay, we have the derivative is dy dx equals 1 over the square root of 1 minus x squared, and say, take it for face value. Okay? But this is the rationale over here as to where it comes from. Okay? And like they say, or what they have in the book, ultimately, okay, if you look all the way at the bottom, okay, because you're using u's, you know, and I was going to use x, so remember we have to also use the chain rule. So the derivative, no, I don't want that. I want d dx, sorry. There's not always a y. Okay, so your d dx of sine inverse of u. Because remember, u is going to represent any expression, anything, 3x squared, 2x plus 1, whatever. Okay, it equals, it's going to equal your 1 over square root of 1 minus u squared. And then here is your derivative of u with respect to x. Okay, so this is the key right here. Now you're going to see how this works, where it all comes into play. Okay, we have plenty of examples. All right, I have a quiz scheduled. Today's what, Tuesday, so someone's due Wednesday, Thursday. Quiz will be Friday, okay, on this. Okay, so we'll have time to practice. All right, so here we go. Here is y equals sine inverse of x squared. Find the derivative. Okay, so you're taking the derivative of y, which is dy dx. Now you're taking the derivative of sine inverse x squared. So you're all the way right here. Okay, so you're taking the derivative, okay, of the sine inverse. What is my u? What will u equal? U equals x squared. So u is x squared. Okay, so, and you plug it right into the formula. These are formulas you're going to have to memorize. So we have 1 over the square root of 1 minus x squared squared. Okay, because it's 1 minus u, so you get u is x squared, times the derivative, which is 2x. And that's your u prime. Because remember, u prime is your derivative, or your du dx, derivative of u with respect to x. And then you would make it 2x all over the square root of 1 minus x to the fourth would be the derivative. So the next one, find the formula for the derivative of y equals tan inverse of x. And yeah, this is also in the book. Okay, following right along, 167 if you want. Okay, so what do we do first? Switch such that you have tan y equals x. That is the inverse function relationship. Now we're going to take the derivative. So you're going to take the derivative of tan y, and you are also going to take the derivative of the x. So what's the derivative of tan? Secant squared y. Remember, anytime you have a y, you got to derive that, which is dy dx. The derivative of x is just 1. So dy dx equals 1 over secant squared y. So now you want to figure out, like we figured out on the other one, cosine y, what does secant squared y equal? So if you, some of you remember, some of you won't remember. So you start with the original, cosine squared x plus sine squared x equals 1. And if you switch them around, sine squared plus cosine squared, no big deal. Okay, it's the same thing. We need to get secant. Secant is what? What's the identity for secant? It equals 1 over what? Secant is 1 over cosine. Okay? So if we have 1 over cosine, that means we have to divide everything by cosine squared x. Cosine squared x over cosine squared x is 1, plus sine squared x over cosine squared x is tan squared x, and 1 over cosine squared x is secant squared. I'm sorry, we should y's, right? But it doesn't matter. Okay, I'll change it. It doesn't matter what variable, x, y, z, r, t, who cares? Okay. So then what we have, just be consistent with the previous one. Okay, I did put the sign in. All right. So you have your dy dx equals, because secant squared is right here. That's what it equals. Okay. So we have 1 over 1 plus tan squared, and I'll make that a y. Okay. And then here, look. Tan y equals x. Therefore, it will be 1 over 1 plus x squared. Okay? I'm going to try to squeeze it in over here. So the derivative, I want to use u. That's what I want to be the same thing that the book has. Equals 1 over 1 plus u squared, and then du dx. I don't know how to get rid of that thing there. So that's 1 plus u squared du dx. Like I said, that's exactly what the book has. So that way, if you're lost or whatever else, what is it? Boom, there it is. Okay? And then, remember, they will start to ask you questions using mathematical terminology. Okay? So we have velocity. Okay, remember we have velocity, we have speed, we have acceleration. Okay? What is velocity? Velocity is a what? First derivative. Okay? So that means we want to find the first derivative of tan inverse square root of t. Okay? So your u, what will your u be? Your u is the square root of t, or t to the 1/2. Okay, either one is fine. Okay. Now in the formula, we need a du dx. Du dx is the same as u prime. So the derivative of, and that's why we made it t to the 1/2, because you're going to have to anyways. Okay. So the derivative of t to the 1/2 is 1/2 t to the negative 1/2. Your basic power. Okay. Which you would rewrite as 1 over 2 root t. Everybody okay? So we're looking for the velocity. So velocity, which again is the first derivative. If you want to make it d du, that's okay. All right, we're using velocity, so we will use the v. All right, so we have the velocity, which is, we have it up above. See right here? 1 over 1 plus u squared. Okay, so we have 1 over 1 plus u is root t squared. Times the derivative, which is 1 over 2 root t. So the square root of t squared, which just gives me t. So the velocity of t is going to equal 1 over, because it's multiplication, you just multiply everything, doesn't matter, 2 root t, 1 plus t. Okay? So far, so good? So that's your velocity. What is the velocity of the particle when t equals 16? So t equals 16, plug in 16, so we have velocity of 16 equals 1 over 2 root 16, 1 plus 16. You have to trust me on this. When you plug it all in, you get 1 over 136. And that's the velocity. And when we get better at this, we understand it, we'll put this more in context of a problem. Okay, say, hey, what exactly does that mean? I'll keep coughing in there. Sorry. Sorry, Devin. Okay. Find the formula for the derivative of y equals secant inverse of x. So we follow along, and what did I do? What did I do earlier? I was trying to be consistent here. So tan y equals x. Okay. So tan y equals x. So we'll say secant y equals x. Okay. So we switched them around, and we have your derivative. So the derivative of secant y. Secant y is secant y tangent y, and I forgot the dy dx. Okay, because then you have to derive the y, and the derivative of x is 1. Okay. So then you have dy dx equals 1 over secant y tan y. And we have this identity. Okay, we have that identity. Tan squared theta, and again, theta x equals secant squared theta. Okay. And again, where is this one? Yeah, moving right along on page 168. Okay, so they show your tan. Okay, they have your tan y, which is, or tan theta, is going to be the square root, and this is your x squared minus 1. Okay, moving the minus 1 over. Secant, we already have as your x. Okay, so it's your x squared. Okay. And then what you have is you have derivative equals 1 over secant y is x, right? Okay, and then the square root of x squared minus 1. What did I do there? Okay. Okay, now, if you look on page 168, you see where they account for the positive, negative, the plus, minus of the square root? Okay, if x is greater than 1, all right, you see how you put it in, it's got the positive value. If x is less than negative 1, you're putting in a negative value. Okay, so it's the negative portion, 1 over. Okay, so if I put in the negative, and there's already a negative out in front of the equation, the negative times the negative is going to make it a positive. Okay, so that's why when you look at the formula all the way down at the bottom, it's going to have an absolute value. So the derivative of the secant inverse of u, and this is on 168, is 1 over the absolute value of u. Okay, because if it's greater than 1, it's going to be your positive. If it's less than negative 1, it's going to be your negative in front of it. So that will make it an absolute value. And then it's the square root of u squared minus 1, and then du dx. And then it shows you absolute value is greater than 1. Okay? And then here's an example. Secant inverse of 5x to the 4th. So here you don't have to, okay, what's secant? Secant is secant tan. You don't have to worry about it because we already took care of it, okay, with the inverse. All right, so you just apply the formula. My u is going to be the 5x to the 4th. My u prime is going to be 20x cubed. So based on the formula there, 1 over. So you have 1 over absolute value of 5x to the 4th. And then you have square root of 5x to the 4th squared minus 1 times 20x cubed. That's the derivative. Okay. So then this becomes 20x cubed all over 5x to the 4th square root of 25x to the 8th minus 1. Notice that I eliminated the absolute value. Why did I eliminate the absolute value? Because no matter what value you plug in for x, any value raised to an even number power is going to be positive. Okay? If it was an odd number, I'd have to leave it. Because negative 2 to the 3rd power is negative 8. Negative 2 to the 4th power, 2, 4, 8, 16, is your positive 16. Okay? So it's always going to be positive. So because that occurs, you can then simplify. So the 20 will cancel with the 5. the cube will cancel with the fourth. So I have 4 over x square root 25x to the 8th minus 1. Okay, and that's your derivative of the secant inverse. Okay. I know a lot, but we're late, so tomorrow we'll start working on these. This is what you want to get down in the last page of your notes. There's a dy. Just make sure, because we're using u's here, just make the dy a du. And this is to get the derivatives of 3 other cofunctions, use cofunction relationship. We can go through and prove all these, but we have given you a good base there. So here are the other 3 that you can put right in your notes.